Okay, so continuing on here, stars, where do they get their source of energy? The big thing here that we want to talk about is fusion, all right? And what we have is an image here showing the proton-proton cycle. It does require high temperature and high pressure for this to happen, all right? So let's actually go ahead and write a few of these things down here. I mean, I have this image here for you to see. But the energy source of stars, right, is fusion. All right, you have proton-proton, which is pretty much just two hydrogen nuclei colliding. Proton-proton cycle. Well, we require high temperature and high pressure for this to happen. The high temperature ensures that we have enough kinetic energy of the particles to overcome the electrostatic repulsion. The high pressure ensures that enough collisions happen to increase the chance of a fusion reaction. All right? Okay. So what we actually end up having here, right, the proton-proton cycle is what we're talking about right here. We have this, it just takes us through, you have two protons colliding, all right, that then end up decaying. You end up producing a positron and a neutrino, okay? That's going to be your beta plus decay. And then we have that deuterium, which you now have just an isotope of hydrogen, colliding with another proton, another just single, just another isotope of hydrogen there, and end up forming helium-3, okay? And you have two helium-3 nuclei, right, colliding, fusing, and forming helium-4 with two protons made as well. So this process releases huge amounts of energy, right, and lots of radiation, okay? So what ends up happening is that you, for stars to exist, we have this really strong outward radiative pressure, but there's so much mass that we also have this huge inward gravitational pressure. And so the idea here is that you need this gravitational pressure in order for us to even have fusion, to create the high temperatures and high pressures. But that once you have that, you end up having this push back out of radiation. So that balance of pressures actually is what keeps a star together, okay? So pretty much just as I explained it there, you have a balance of radiative pressure and balance of gravitational pressure as drawn on the previous page. So what ends up happening, all right, you have a lot of energy emitted, and the energy that we emit per time, instead of calling it the power of a star, we call it the luminosity, all right? And so the luminosity is just the energy emitted per time by a star. Okay? And the two things that it depends on, based on actually Stefan-Boltzmann law, right, is the temperature of that star and the surface area. Okay? So this, gets at this equation right here. L instead of P equals the Stefan-Boltzmann constant times the surface area times the temperature to the fourth power. That's the equation that we'll be using when we study this. Okay? So the important thing here, right, we're going to get to this in a little bit, is that mass actually effectively ends up determining that luminosity. Okay? So the importance of mass is that it determines just how bright a star is, right? And that gets at that whole idea of gravity, okay, and how much it's going to pull in there and how much fusion is going to end up happening. All right. So here, just to show you have a high mass star, a very, very massive star is going to be producing lots and lots of helium, all right, from that fusion process. A sun-like star, okay, producing a little bit less, and therefore being at a lower temperature. Here we have a blue going to yellow, and then going to a red star with very low mass and not as much fusion that are being producing radiation. Okay, so there's just a few equations that we need to be aware of here. The surface temperature, all right. This is Wien's law. We've already talked about this. but we're going to be using this equation a lot in this chapter to determine the surface temperature. And the reason is that we can look at an emission spectra, determine the peak wavelength, and use Wien's law to help us tell us what the surface temperature is going to be. Okay, so that's the comment that you want to make right here. We observe the peak wavelength, okay, and we use that to determine the surface temperature. All right. So for luminosity, Stefan-Boltzmann equation, like I had mentioned before, all right, and assume it to be a black body. All right, and that's the Stefan-Boltzmann equation. Okay, and apparent brightness, this is a new term that we're going to use here. It's just going to tell us that luminosity divided by the surface area. All right, so it's basically an intensity, which is what the apparent brightness is. And d is going to be the distance, though, from the star, so wherever you are observing it. And so, again, this is just what we're calculating here. This is just the intensity based on how far away you are from the star. All right? So we can do some sample problems here, just to show you, you know, what you'll be doing. And a lot of this stuff we've kind of already done in terms of the equations when we did energy, power, and climate change. Okay, so the first problem here, all right, that we're going to look at is that we get the sun. It's a distance from 1 astronomical unit from the Earth, right? We want to know how much sunlight falls on an area of 1 meter squared in a year. So, you know, what we're looking there is to get the apparent intensity, apparent brightness, and then solve for just the energy. All right. So we already know, we can calculate that the luminosity of the sun here, and that's my sun symbol there, is just 3.9 times 10 to the 26th watts. Okay, and that the surface area over which this is distributed is 4 times pi squared times, 4 times pi times d squared, right, which is just the distance from the sun there. So we can calculate the apparent brightness, right? It's just this luminosity here all over the area, and when we do this, we end up with the following, and this many watts. There we go. 1,378 watts per meter squared, ignoring sig figs as I usually do. And let's see here, and we want to know the total energy that we end up receiving, okay, which is just going to be energy equal to the apparent brightness times time times the area, all right? So this is just going to come down to this times this times that area that we had from before, which is just, they're not going to rewrite that, and we end up with this many joules falling on 1 square meter in a year. Okay? So if we know that the sun is approximate black body peak wavelength, all right, of, let's see, 500 nanometers, all right, we can find the surface temperature just using the Wien's displacement law, all right, or Wien's displacement law, and we do that. This is how we say, you know, the surface of the sun has a temperature of about 5800 Kelvin, right? Okay, so let's try another problem here. Moving down. All right, so this is a fun one. This is a common type of IB style question. All right, they tell you the radius in terms of, you know, 2 different stars, comparing it, not giving you any numbers, and the temperature in terms of both those stars, and then we're supposed to find the ratio of the luminosity of A to B, okay? Well, we know that luminosity, we can rewrite this, right, as the Stefan-Boltzmann constant times the surface area times the temperature to the 4th power. We know that the surface area is just going to be 4 pi r squared, r being the radius of the star, right, temperature to the 4th power. So you see here that the only 2 variables that luminosity depends on are r and t, so if we know what r is in terms of both stars and t is in terms of both stars, we can have those numbers end up canceling out and just be left with a constant proportionality between the 2. And so what I mean by that, and I'm just going to write this out here, okay, is that the radius of A, right, is equal to 3 times the radius of B. And then see here, the temperature of A is 2 times the temperature of B. All right, that's what's given in this first sentence. You should be able to tease that out. So we're just looking at the ratio of the luminosity of the two stars. All right, we're going to plug everything in here. And let's see here, it's going to be R A squared T A to the fourth. Alright, and then we can just substitute in all of our values that we have here on the top. Cancel these out, make life easier. Alright, so we end up with 3RB squared times 2TB to the fourth all over RB squared and TB to the fourth. Alright, so our RB and TB are going to cancel out, and the ratio that we're left with here is that it's going to be 144 to 1, comparing luminosity of A to B. Alright? So there we go, another fun sample, typical IB problem. And let's try one more here. So we have a star, has half the sun's temperature and 400 times its luminosity. We want to know how much bigger it is. Alright? So you're going to do the same thing again here. 400 is equal to the ratio of some star and its luminosity compared to the luminosity of our sun. So again, I'm just putting all this in. Alright, so there we go. And we know that it's temperature. Let's see here, it says it's half that of the sun's. Okay, so we can substitute that in there as well. And so what we end up with here, alright, is R squared times T sun to the fourth, over this R. And so what we end up with is this. Keep writing with that. Okay. And let's see here. Yeah, so it's going to be, this is all equal to 400 still. So 400 is equal to that, and then just multiply 16 over, so 6,400 is be equal to R squared over R the sun squared. Alright, so we end up with the R over R the sun is equal to 80. So the radius of this star is equal to 80 times that of our sun. Alright? Yeah, another typical IB style question. So last piece here that's important, alright, is that I have a great image here of the different black body spectra of a low temp star, typical average star, and a really, really hot, blue giant type star, alright? And what's important, okay, is that this black body spectrum here, it gives us two different things. It gives us the luminosity and the temperature, alright? We get the luminosity from the fact that we know exactly how much we're receiving here, all right? And if we know how far away the star is, we can figure out the luminosity, okay? And so we don't exactly see this, though. We actually see the absorption spectra, okay? And so I'm going to show you what that looks like here in a little bit. All right, this is the black body spectrum. We see the actual absorption spectra with some lines missing there. So right now, that's just to get us started here in terms of some data about stars, some characteristics of stars. Next section we're going to get into is the classification of stars based on their spectra. All right.